Thank you very much, Yasha, and thank you very much, Thierry, for inviting me and having me here. I was very surprised by the invitations, since I basically don't know anything about Tom's works. And I discussed a lot with Marie-Claude Arnaud, who unfortunately is not here, but she convinced me that I should come and give this talk today. So I will talk about a joint work with Vincent Colin, Pierre Dehornoy, and Umberto Hryniewicz. It's been an ongoing collaboration for the last few years. And I'm going to talk about flows on three-dimensional manifolds. So choose the three-dimensional manifold you want. So along the top, M will be a close-oriented three-manifold. And I'll be always working with, will become Reeb vector fields in a while, but just for the moment, just think about non-singular vector fields. And somehow what I want to say is I want to study this three-dimensional flows, so that parameter by R dynamics from a surface dynamics. So the best thing that can happen from that point of view when you have a flow in this thing is that you find a section. So what I mean by a section, you find a surface, closed surface, that is transverse to the vector field everywhere, and that crosses all the orbits. So the best thing that can happen from some point of view is you have a cross section. So you have a section. So the best thing, let's say this way, is to have a section. So some embedded surface without boundary that is transverse to the vector field and intersects all the orbits. So why I say the best thing is because then you can look at the first return map of your flow. So you take a point, you follow the orbit, and you see where it comes back to the surface, and then you get a diffeomorphism of the surface. And studying, if you don't care about the parameterization, studying the flow becomes studying this diffeomorphism of a surface that is a priori simple. Okay? This almost never happens. Okay? The first reason is that if you have such a thing, this three manifold has to fiber over the circle. Okay? And the flow has to be very special. Okay? So let me just go to another example of a simple flow where this doesn't happen. I think I learned this example from Etienne the first day I had a classroom. I was in a classroom with you. So take the half vibration. So take S3 with the half fibers. Okay, so you know it's the vibration by circles of S3, and if you take any two circles, they form a half link, so they're length 1. Okay, and then you have circles everywhere. I mean, imagine all of you have seen pictures of the half vibration, and then take a flow that is always tangent to this, and all the orbits have, let's say, the same period 1. Okay? There's no section, because S3 doesn't fiber over S1, but there is something similar. If I take the disk that is bounded by one of the periodic orbits, it is almost as a section. So it's a disk, so it has boundary. The boundary is tangent to the flow. The interior is transverse, intersects all the orbits. So I still have a first return map. And this is what we call a Birkhoff section. So let me just say the definition. So what I want is, so a surface with boundary that I would just, this one is embedded, but I will just ask to be immersed in M, and such that the boundary of S is mapped to a collision of periodic orbits. The interior is embedded and transverse to the vector field, and it intersects all the orbits in finite time. Okay, so now having a Birkhoff section, what it tells you is that your manifold admits an open book decomposition, because if you take out the boundary of the section, so this is a link, the complement will fiber over S1, and the fibers will be all these surfaces that give you an open book decomposition. Okay, so I will talk about Birkhoff sections and open book decompositions in a while. It still being very good. It still gives me a surface with boundary, with a diffeomorphism that is well defined in the interior, that catches all the dynamics of the flow. So I'm very happy if I have something like this. So the theorem I want to explain today, it was obtained by two parallel teams of people, so Gonzalo Contreras and Marco Mazzucchelli on one side, and Colin, Dehornoy, Hryniewicz, and myself on the other side, was maybe last year, is that among Reeb vector fields, so the set of Reeb vector fields that admit a Birkhoff section contains an infinity dense set. Okay, so I still have to define Reeb vector fields, but I think that other than that, so there is this family of Reeb vector fields, and among them, having this section is
contain mean itself city infinity dense. Why contain?
Because it can be everything.
What?
It could be everything, no? Well, I don't know.
Okay.
I don't have any example that doesn't have a Birkhoff section. So it could be everything, a priori. Well, it's infinity dense, if you want. I can put is, but I don't know. So my first comment is that I don't know if it's everything. It could be everything. I don't have any counterexample to a Reeb vector field without Birkhoff sections. Okay, so let me start with the definition of a Reeb vector field.
I'm sorry, because dense is a set of all that is
Among Reeb vector fields, yes. Everything is among Reeb vector fields, yes. Yes. Any more questions about the theorem or corrections? Okay, so let me just give quickly a definition of the Reeb vector fields for those who don't know them. So let me define a context structure is a non-integrable plane field over the manifold. But if I know that, will know by C. And as such, it can be defined as the kernel of a differential one form alpha and this non-integrability condition tells you that if you take the product of alpha with the alpha, this is never zero. Okay? And to the alpha, you can associate a vector field. It's called the Reeb vector field. Of alpha is defined by the following two equations. It has to be on the kernel of the alpha, that is a one-dimensional distribution, and you normalize it by asking that alpha of x is equal to 1. Okay? So just let me make one remark. It's not defined by the contact structure, it's defined by the contact form. You can change the contact form and you will change the vector field. Okay? If you multiply alpha by any non-zero function, you get another contact form for the same contact structure with another Reeb vector field. Okay? So to one contact structure, you have a lot of vector fields to associate. Okay? So examples of Reeb vector fields are geodesic flows. And for example, in the restricted planar three-body problem, all the levels up to the first Lagrange point are Reeb vector fields. And so these are this big family of volume-preserving vector fields on dimension 3. Okay. Okay. So now that I have no idea of the time. Okay. So now that I have all the definitions in place, let me just do a few remarks. Maybe. Both on the theorem. Okay. So the first remark is that Reeb vector fields cannot have sections. Okay. The reason is that if you have a surface that is transverse to a vector field, then d alpha will give you an area form on the surface, and if the surface has no boundary, you have a problem by Stokes' theorem. Okay? So the best you can ask in this family of vector fields is to have a Birkhoff section. The second remark is Emmanuel Giroux has this very powerful theorem where there is a strong relation between open book decompositions and contact structures. Okay? So what Emmanuel Giroux tells you is that for each contact structure, you can find at least one Reeb vector field that admits a Birkhoff section. Okay? There exists a Reeb vector field. Okay. The third remark that I'm going to make is that if you have a Birkhoff section, then you have periodic orbits. So I'm not claiming that we have a new proof for periodic orbits. This was already known. So Reeb vector fields have periodic orbits, always in dimension 3. So the existence of one periodic orbit was proved in full generality by Clifford-Tubbs. In 2007. And we actually know that there is at least 2 periodic orbits. And this is Christopher Gardiner. And Michael Hutchings. In 2016. It is conjecture that a Reeb vector field has always 2 or infinitely many periodic orbits. Okay. Now I want to comment on that infinity dense. So let me comment the generic hypotheses are in this theorem. So I told you there's 2 teams of people, so there are 2 sets of hypotheses. They're not the same. So what Contreras and Mazzucchelli did is that they proved that a Reeb vector field has a Birkhoff section under the following hypothesis. So for Reeb vector fields, they are non-degenerate. And it's what I call strongly non-degenerate. And let me tell you what it is. So when you have a vector field and you can look at the periodic orbits and look at the Poincare return map for each of them. And these are volume preserving, it's a volume preserving flow. So when you take the differential of that map, you get a 2x2 matrices of determinant 1. So you either ask it to be hyperbolic, so to have real eigenvalues, or if it's a complex eigenvalue, I will ask that it's an irrational rotation. Okay, so this is the non-degenerate part. And the strongly thing is, if you look now at the hyperbolic periodic orbits, you have stable and unstable manifolds, you will ask these intersections to be transverse. So what they did is, under this hypothesis, you can find a Birkhoff section. And what we did is, we still need the Reeb vector field to be non-degenerate. And we need equidistribution of periodic orbits. So what this means is, so you have an invariant volume and you want to have invariant measures that are supported on periodic orbits that tend to the invariant volume. Okay, so you have this more and bigger collections of periodic orbits that eventually get as close as you want of the invariant volume. Okay, and this is a infinity dense condition, or infinity dense, by work of Hryniewicz. It was published in 2021. I want it up here. So this is the 2 sets. So what I want to explain is, so the 2 proofs are quite related. I mean, the strongly thing or the key distribution, they appear to find something that is similar in both. So I will try to explain where the proof came from, and if I have time, then to say some of the implications of this. Okay. So there's one word I haven't used on the title, and that's broken books. So the construction of these Birkhoff sections, or open books if you want, comes from broken book decompositions.
But Birkhoff section give you automatically almost open book, not broken, right?
Yes. But to build this Birkhoff section, I have to start first by a broken book. That's the way I know how to do it. Yeah, if I have this, I have an open book, much better, much simpler, but I don't know how to do it directly. Okay, so broken book decompositions. And the theorem that I'm going to use, it was proved by Vincent, Colin, Dehornoy, and myself, published this year, is that every non-degenerate Reeb vector field is supported by a broken book decomposition. So let me draw a broken book decomposition. Fine. Yeah, we'll just draw one and then explain a bit more. So let me go back to S3. Okay, so in S3 I had the half vector field that is just in the blackboard behind, and I told you we have a disk. Okay, so let me draw this open book in a two-dimensional manner. This open book. So for S3 with the half, let me redraw what I draw with the circles on the disk. I'm going to cross the circle with a plane, just at 2 points. So you have to think these 2 points are in a one periodic orbit that comes out here, goes into the blackboard, and then makes half a turn behind. And my disk will be a line. And what it says is that you can push this to be an open book decomposition, so you can push little by little the disk to cover all of S3. Okay, so this gives you an open book, the simplest open book decomposition of S3. We're good with the picture. Now let me do a broken book decomposition of S3. So now take, instead of one circle, we're not longer the half flow, just S3. Take 3 parallel circles, okay, like in a cylinder. And I cut it with my plane, so I have 3 pairs of circles that I'm cutting each on 2 points. Okay, and then I'm going to fill the rest of the picture. Let me do it like this. So I have 3 circles, and I'm going to foliate the rest of the manifold, the complement of the S3. And so the vertical line, so you have to think, so everything turns with respect to this line 180 degrees. So these two lines belong to the same leaf, and it's just a cylinder that goes around. As all the leaves that are here are just cylinders, and this one also, and then the rest are discs. Okay, so a broken book decomposition will be a link. Here is the 3 circles, and then a foliation of the rest, but not any type of foliation. When we go to the link, we have 2 possible situations. Then either we have the radial foliation, as in the open book case, either we have what we call the broken components. Okay? So either you have the radial foliation, this is what happens at the top and the bottom circles on the figure over there, or you have some components, or that we call the broken components, where you have some radial leaves that separates 4 sectors that are foliated locally by what I call hyperbolas, but they're not hyperbolas, just leaves that come close and go out without having a boundary there. Okay, so these are the 2 possible situations near the binding of my broken book. Okay, and then what means to be supported? So I have a broken book decomposition, I have a vector field that is supported by it, so I want it to be tangent to the binding and transverse to the interior of the leaves. Okay, so if I put a vector field here, you put a direction somewhere, then you follow it. Gives you everything that is happening. Okay, and this is a non-degenerate vector field, so the broken components of the binding have to be hyperbolic periodic orbits, and so they have a stable foliation, a stable manifold, sorry, and an unstable manifold. Okay. So let me point out a few things. So in this picture, and what happens in a broken book decomposition is you have a finite set of leaves. So the ones are in orange, that we call the rigid leaves. When you take the complement of that, each connected component is fibers over R, and this fibration is exactly the foliation you have. So you have this more important leaves somehow that divide your manifold into things that are simple from the dynamic point of view. Okay? And so if you have an orbit, it will go around and we're crossing this rigid leaves infinitely many times, except if it belongs to the stable or the unstable manifolds of one of the parts or in the broken part of the binding. The rest of them will be just going from one rigid leaf to another, etc. So this set of rigid leaves is like a set of transverse sections that cuts all your orbits, and you could follow it. I mean, a priori you can follow one from the other and see where the diffeomorphisms, except that you have this stable and unstable manifolds that get into trouble. Okay. So how are we doing? So let me just say what are the ingredients of the proof of the existence of broken book decompositions. I won't go into the proof. So this is maybe for people that know more, but the main ingredient is embedded contact homology. And the other big ingredient that is applied several times along the construction is what we call Fritz techniques. On transverse surfaces, transverse to a vector field. So embedded contact homology just provides a lot or enough transverse surfaces that are not embedded. So you have to make them embedded. And this is the first time when this comes in. And then you have to pick some of them out to build the broken book decomposition. So I want to say a few words of this because it will come out when trying to explain you how to prove the theorem. So now let me go back to the simple half flow on S3 that is a degenerate right vector field, but still it's one I understand. So I go back to S3 with the half vector field. And I told you if you take any orbit, it's a boundary of a disk that is transverse to it. Now the question is, take a finite collection of periodic orbit, does it bound a Birkhoff section? And I want you to convince you that at least if you take all the multiplicities to be 1, it is true. So then you have a disk. This is another periodic orbit that passes for infinity. And it bounds a disk that is also transverse to it, to the flow. Okay, so I have my half length and I have two disks that intersect, and they intersect along a line of double points. So I have this line of double points. Okay, and if I look transversely at what is happening, so I have the orange disk and I have the green disk, and then in some direction I have the flow that is transverse to both. And if I want to get rid of that intersection, the only thing I can do is to do this. Okay? But then I get to the boundary. Okay, so what happens in the boundary? Well, it happens that just the obtained surface will go around. Okay? One way of visualizing this is that you can blow up this orbit. And if you blow up the orbit, you replace it with a torus. Your vector field extends to this torus just by linearity, and then you have the trace of the Birkhoff sections that are like this. But then I undid the intersection, so now my new curve will do like this. Okay, and this still transfers to the vector field, and then you can collapse it back to the boundary. Okay, and so when you get out from this to circle, from this to disk, sorry, it's an annulus. Okay, and this is, I don't know, so the Frid sum of the two disks gives you an annulus. And also, that's still, it's a Birkhoff section. Okay, and you can do this with all the disks you want, and you just undo the intersections one by one. Okay. So now let's try to prove the theorem. I want to tell you the strategy and then give you, oh, this is clock over there, and give you something. So the theorem we proved with Vincent Colin and Pierre Dehornoy tells you that you have this broken book decomposition. Okay, so this broken book decomposition fails to be an open book because of those broken components. Maybe they aren't. So if they aren't, we already have a open book decomposition and we're happy. So now we want to get rid of these broken book decompositions. How do we get rid of this broken book decomposition? We find surfaces that are transverse to them. Okay, transverse surfaces are transverse to them. So I want to try to explain a proof for geodesic flows that I think people are more familiar with, and then see if we go back to the thing. Okay, so maybe one thing to say now is, why are they called Birkhoff sections? And they're called Birkhoff sections because they were built by Birkhoff for many geodesic flows. Okay, in particular, they were built for positive curvature spheres. So you have S with some metric of positive curvature. Okay, so if you have S2 with a metric of positive curvature, you have an equator. So you have a geodesic that, if you want to think of an ellipsoid of revolution, think of S2 as one. You take one of these geodesics on S2 and you can orient it in two directions. So the geodesic flow that lives on the unitary tangent bundle of S2, so the geodesic flow is on T1 S2, and it has at least these two periodic orbits that are given by this geodesic. Okay, now what Birkhoff says, take all the vectors that are, take a point here, any point in this, and take all the vectors that point toward the north hemisphere. Okay, so you take all the unitary vectors that are either tangent or point in the north hemisphere. Okay, and you do this for each point of your geodesic. This in the unitary tangent bundle is an annulus. Okay, it's a circle cross an interval, and is transverse to the flow, tangent in the boundary, and intersects all the orbits. Okay, if you're in positive curvature. Okay, so this is what we call a Birkhoff annulus. Okay, so now let me try to give you a proof for geodesic flows, or a non-proof maybe. I don't know how to do it. I should have numbered the theorems. Of theorem on Birkhoff sections. For geodesic flows. So start with a Reeb vector, so with a geodesic flow, it's a Reeb vector field, and assume that it's non-degenerate. You have bumpy metric, it's non-degenerate. Okay, so the theorem that is on your right tells you that it's supported by a broken book decomposition. Okay, well, it has broken components. Okay, these broken components are hyperbolic periodic orbits, and I can project them down to my manifold, to my surface. Okay? So your flow here, phi t, is supported by a broken decomposition and you suppose that there are, so I will not KB the broken binding. And suppose KB is not empty. So now you project KB. So in your closed surface, whatever it is, you get some collection of periodic orbits. I will just draw one. Okay? If it happens that you can find, by some reason, you can find another periodic orbit that is not part, let's say, I can find another periodic orbit, another geodesic. Okay, so suppose that there exists a closed geodesic that intersects P of KB. And so when I take the two, and such that if I take the two periodic orbits of the geodesic flow that cover this geodesic, they are not in the binding. And such that, so pi minus 1 of gamma as periodic, or let me say gamma plus and gamma minus, the periodic orbits of the geodesic flow are not in the binding. I don't know where. Then I can do what Birkhoff did and take the Birkhoff annulus over this. Take a Birkhoff annulus. So choose one of the sides and take all the things. So what this gives me in T1 of my surface is an annulus that intersects this KB. Let's say that intersects is positive. I choose the side of the annulus that intersects is positive. Okay, so now I want to use Frid to add this thing to my set of rigid pages and get rid of the broken component. Okay, so you get an annulus. So you get A gamma, the Birkhoff annulus, over gamma that intersects positively. I will say KB, but just, let's say, each component of KB. Okay? And then the idea is to add A gamma to the broken book decomposition. To obtain an open book decomposition. Okay, so you add this surface that is transverse to the thing, and then it makes all the surfaces go around enough to be not to be broken. Okay. So the thing is, you have to find this gamma, and I won't say how you do it. Okay. So let me go back to the theorem, maybe, and then I will stop. So how you do it in general for Reeb vector fields. That's how you can do it for geodesic fields, Reeb vector fields. So you want to find, basically what you need to find is a surface that is not necessarily everywhere transverse, but intersects all the orbits and the broken part of the binding positively. And once you do that, you can add it. And since everything else is transverse, then you can make it transverse somehow. Okay? And the way we did it is with equidistribution of periodic orbits, because then you get something that is positively linked with KB. Okay? Okay. So for the last few minutes, I just want to give some consequences of these theorems. So the first thing is that once you have a broken book decomposition for a Reeb vector field, it's not very difficult to prove that every non-degenerate Reeb vector field has either two or infinitely many periodic orbits. The second thing I want to tell is about once you have a Birkhoff section. So if you have a Reeb vector field that is strongly non-degenerate, and whose periodic orbits are equidistributed, then we can prove, and this is on being written, every hyperbolic periodic orbit has a homoclinic orbit. So it means that all the stable and unstable manifolds intersect, okay, for every hyperbolic periodic orbit. Okay, so then I will stop here. Thank you very much.
Questions? So, you mentioned that you don't know any example of Reeb vector field before. Do you have it's possible it's not Reeb vector field, but just any divergence free vector field. Do you know how many examples? They just with a closed form and you can do it.
I have C1 counterexamples because I have examples without periodic orbits. So if you have divergence free. Quoi? Le tort.
What?
Linear flow torus.
But without periodic orbits.
Yes.
Yeah.
And second, do you have any bound on the length of the
Yes. Yes.
Yes?
The orbits in the binding.
Yes.
Yeah, they are bound by the first ECH capacity.
So then why you cannot pass to the limit? You have compactness, you have a sequence of like this for converging to some. That's why you cannot pass, because then you have all the section and it's bound, and it kind of seems likely that you can choose something convergent. No.
We've been trying. I mean, I don't know. Maybe it's just that I don't know enough. But we've been trying to do that. We haven't. Yeah, but it's bound. I mean, the only thing you need is a collection of periodic orbits where the U map is non-trivial, and that's what you need.
Okay, thank you.